Hello, my name is Fillipp Edvard Salvador. I am an undergraduate researcher at New Mexico Tech, and I am presenting my research on the mechanochemistry of hafnium and zirconium-based metal organic frameworks. I will begin by introducing what metal organic frameworks are. They are a crystalline porous material made up of metal nodes and organic linkers. The characteristic property of MOFs is their large surface areas in relation to their mass. This property, along with their high degree of tunability, lends to their usage in a wide variety of applications. For example, a MOF can be designed such that it favorably binds with gases such as hydrogen or oxygen. Such a MOF can increase the storage density of conventional pressurized gas tanks by increasing the volume of gas that can be stored at a given pressure. A MOF that is designed to have a higher affinity for one gas over others can be used to separate it from a mixture of gases. For example, a MOF that favorably binds oxygen over nitrogen and other atmospheric gases can be used to prepare pure oxygen. This would be a cheaper and greener alternative to the conventional cryogenic distillation method of preparing oxygen, which requires extremely low temperatures and specialized equipment. Additionally, the porous nature of MOFs make them great catalysts. It exposes more surface area where a reaction can be catalyzed. MOFs can even be used as drug delivery systems. They can be designed to be biocompatible such that once they have reached the target system, they can decompose into harmless components to release the drug. The conventional method of creating MOFs is through solvothermal and hydrothermal synthesis. These methods involve using excess solvent or water and heating the reaction mixture for an extended amount of time. This is not ideal because not only does it require a lot of energy to reach the necessary temperature, it also contributes to the amount of volatile organic compounds and other pollutants already in the atmosphere. This takes away from the possible environmental benefits that MOFs may have. An alternative synthetic method is mechanochemical synthesis, which uses mechanical energy to aid in the formation of the extended MOF material. This method uses little to no solvent and less energy than the conventional method. Studies have used the synthetic method to recreate already known MOFs. We also synthesized a family of hafnium-based MOFs. We used different organic linkers that allowed the MOF to assemble into different crystal structures. For this mechanochemical synthesis, we loaded the starting material and a very small amount of solvent into a Teflon capsule with Teflon balls, then placed the capsule into a ball mill. The ball mill shook it around to provide the necessary force to form our extended material. Here you will see the different organic linkers we used and their associated powdered X-ray diffractions. We then compared one of our mechanochemically synthesized MOFs, hafnium UiO66, with its solvothermal counterpart. The mechanochemical MOF has a PXRD that matches both the solvothermal and calculated patterns, and the adsorptive capabilities of both mechanochemical and solvothermal MOF are comparable. We then synthesized a family of multimetallic hafnium zirconium MOFs, both mechanochemically and solvothermally. We found that mechanochemical synthesis allows for the formation of a unique family of multimetallic MOFs with metal precise clusters. To elaborate, the mechanochemically synthesized hafnium zirconium MOFs retain their single metal hafnium and zirconium clusters, while in the solvothermally synthesized MOFs, the hafnium and zirconium clusters rearranged into the mixed metal hafnium zirconium clusters. This conclusion was drawn from the extended X-ray adsorption final structure, or XAPS, data of mechanochemical and solvothermal hafnium zirconium UiO66. Here, the top figure shows the zirconium K-edge XAPS data, and we have highlighted the key areas. The strong signals of the single metal zirconium UiO66 and mechanochemical hafnium zirconium UiO66, blue and red respectively, at 3.1 angstroms, represent the strong zirconium-zirconium scattering found in single metal zirconium clusters. The solvothermally prepared multimetallic MOF has a much weaker signal because its metal cluster is rearranged to form mixed metal hafnium-zirconium clusters. The bottom figure shows the hafnium L-edge XAPS data. Similarly, the single metal hafnium UiO66 and mechanochemical hafnium-zirconium UiO66 have strong signals at 3.1 angstroms, which is due to the hafnium-hafnium scattering. The solvothermally prepared MOF does not. These two pieces of information together show that mechanochemical synthesis allows for the creation of multimetallic MOFs with metal-precise clusters. To summarize, we report an effective mechanochemical method of synthesizing hafnium cluster-based MOFs, and also demonstrate that mechanochemistry allows for more control in the distribution of metals in multimetallic MOFs that the solvothermal method does not afford. I would like to acknowledge the following for making this project possible. Thank you for your time.